Okay, so welcome back. We're about to move into our second test for series convergence, which is a little more powerful, but requires a little more computation. But before we do that, I do have one more remark I want to make about series convergence. So for series convergence, and this actually harkens back to a principle with improper integrals that we had. So the convergence of a series doesn't depend on any of the beginning terms. Okay, so the convergence or divergence of a series doesn't depend on the terms at the start. Okay, it only depends on what I'll call the tail of the series. Okay, and so in other words, we have pictures. Okay, so if my terms are, they can really do whatever they want to do, right? They can act in a very crazy way initially, but all we need is that eventually very far out we need the terms to settle down and approach zero. So we don't care. All kinds of weird stuff can happen out here, but we just need the terms to eventually converge to zero quickly enough so that the partial sums can converge to some number, or we examine that the terms are eventually not ever settling down. And so let me even phrase this a little bit differently because I don't want to create confusion with the divergence test. So what I'm trying to say here is the behavior of the series, right? It could be, so let me put it this way, right? If that these are two possible endings to my series, right? It could be like these blue dots I've drawn in here, or it could be like these brown dots here. And both of these series that I'm indicating here might start with the same dots that I've depicted at the beginning, but what distinguishes between one of these converging and one of these diverging is the tail, so what's happening in the limit. So that's the main point I want to make, is that when we think about series convergence, we really look at the tail. And that's kind of like when we look at an improper integral, what we're concerned with is what the function is doing if it's an improper integral over an infinite interval, right? So it's going off to infinity or minus infinity. What we care about is the end behavior, not so much the behavior at the beginning. And the same principle is true for series. So we're going to move into the integral test for series, and so I'm going to actually go through the example your book does in activity 8.3.5. So feel free, if you'd like, to go ahead and stop the video here and take a look at that activity I'm just going to go ahead and draw some pictures here coming up and talk about those results. But if you'd like to go ahead and pause the video here, you can rejoin in just a moment with what you've worked through with that exercise. Okay, so just starting up here, we want to investigate. So the motivating example here is the harmonic series. So as we're thinking about the harmonic series, you'll remember that when we looked at a graph of the partial sums, it wasn't clear what was happening. When we look at a graph of the terms are certainly approaching zero. So let me go ahead and I'm just going to sketch this. You have a much nicer picture in your book. And in fact, okay, so 1/2, 1/3. Okay, so we've got 1, 1/2, 1/3, 1/4 is about maybe right here, and then 1/5, and so on. And so this is decreasing here, and what I want to just comment is, okay, so the harmonic series is the terms of the harmonic series are 1, 1/2, 1/3, 1/4, and so on. And the function that actually goes through each of these terms is the function f of x equals 1 over x. And so that actually goes through each of these. And so the helpful observation here, so we'll notice that these are going to zero, so we couldn't apply the divergence test. So the helpful observation here is that if I draw boxes, and this kind of harkens back to Riemann sums, right? If I draw boxes, so notice that when I plot these terms, I have 1, 1/2, 1/3, right? When I'm plotting them horizontally, they're separated by a distance of 1 apart because the counting numbers are distance 1 apart, right? And so, so 1 plus 1/2 plus 1/3. So what I'd like you to notice here is that the area of this first box is exactly equal to 1. And the area of the second box is equal to 1/2, right? Because the width is the width of the box is 1. The area of the third box here is 1/3. The fourth box has area 1/4, and so on. So so the point is that here's the big observation then. Observation here is that the sum S7, right, and I've sketched it here, and so this is equal to 1 plus ... plus 1/7, right? This is greater than or equal to the integral of the function 1 over x from 1 to 7, right? And in general, S7 sorry, not S7. In general, Sn is greater than or equal to the integral, so of 1 over x dx from 1 to n. So we know from our investigation of improper integrals, we know that the limit as n goes to infinity of the integral from 1 to n of 1 over x dx, there's an infinite amount of area here. That's infinite. And so since Sn is always bigger than this corresponding integral, then the limit as n goes to infinity of Sn has to be greater than or equal to the limit as n goes to infinity of the corresponding integral. So so we could say either that this limit is infinite or it doesn't exist. In either case, what we know is that what we know here is that that this series therefore diverges. So let me go ahead and add a new page here. I'll make sure I add a corresponding page to your notes. Okay, so hence the series 1 over x, sorry, not 1 over x, I want to use an indexing variable here, so 1 over k hence this series diverges. Now we already knew that by a direct calculation, but the point here is that this correspondence actually is true in general, right? So I want to show you kind of a more general picture here. So if we have any old function, well, maybe another way of describing this, let me go ahead and just write on my previous function here. So let me just grab this, copy, paste another copy here, just, whoops. Just to not clutter up the previous notes here. Let's get rid of that. So notice that in fact, if we had drawn the boxes just to the opposite side, right? So if I had drawn the boxes so that the right endpoints, right, if this is a decreasing function and I draw the boxes in this way, much like we saw with Riemann sums, all the boxes will be below the curve, right? And so here, right, notice that the sum from k equals 2 to infinity of 1 over x is less than the integral from 2 to infinity of 1 over x dx. This is less than the integral from 1 to infinity of 1 over x dx. Right, and I'm going to go ahead and put less than or equal to, it's strictly less than, but okay. So what this is showing is that the sum from 2 to infinity has to be less than this improper integral here, and so, okay, of course, now we already knew that this improper integral diverges, right? So knowing that a sum is less than something divergent doesn't tell us a lot, But let me suggest that if we didn't already know that that this improper integral diverged, right? But we knew that the harmonic series diverges, right? Well, divergence only depends on the tail of the series. So subtracting 1 from something that diverges isn't going to make it converge. So if we know that this series is infinite, then that also would give us a way of showing that that the integral on the right hand side here also diverges. Okay, so what is the upshot of all of this? The upshot is that if we have a decreasing function like 1 over x, although it could be really any function, and we'll use this for other functions, then because the function is decreasing, right, then if we draw boxes to the left and right, the area under the function is sandwiched in between the red boxes and the blue boxes. So let me just write that in general. In general, if f of x is a positive decreasing function, then the area represented by the integral from 1 to infinity of f of x dx, right? So that area is the area under the curve. Okay, so I guess maybe I can highlight here in black. Let's see, that's this highlighted in black area, right? That's the improper integral here. Okay, so that area is sandwiched between the red and the blue areas. And so on the graph there. So let me go ahead and write that more specifically. The area, or the improper integral from 1 to infinity of f of x dx is always going to be less than or equal to the sum from k equals 1 to infinity of f of k. Okay, and so note here, I'm still using f of k. Here, if k is 1, 2, 3, 4, then we have f of 1 is just the height of the curve at 1. Right? F of 2 is the height of the curve at 2. In this case, that's 1/2. But this works in principle for any f. Okay, and then so this is the blue area here, and that is also less than. The improper integral is greater than the sum. If we start at, oops, okay, I think my pen just might have run out of battery here. Yep, it says Apple Pencil at 0, so I'll let this charge for a couple more seconds so that I can finish this. Okay, so the charging is actually pretty good here. So we'll sum from k equals 2 to infinity f of k. Right, so this is actually a pretty key fact here. I'm going to go ahead and have to add one more page, and just so that we can get a clear statement of the divergence theorem here. So, so because it's the case that that for any positive decreasing function we can sandwich the areas in these ways, then what's the upshot? The upshot is then the series
and the integral either both converge or both diverge. Okay, and oops, I didn't put in here the series and the integral 1 to infinity f of x dx. Either both converge or both diverge. Okay, so let me just recap why that is. So so in cases, if f of x, if the improper integral diverges, okay, so why? If the integral diverges, then the sum from k equals 1 to infinity must also diverge. Okay, I'm using shorthand here, so I'm not, okay. Well, I'll go ahead and not do the shorthand. And then the sum from 1 to infinity of k diverges. And if the integral from 1 to infinity of f of x dx converges, then the sum from k equals 2 to infinity is less than that. And so that sum converges. But, okay, if we just add in f of 1, so that doesn't change convergence because f of 1 is just a number. So the sum from k equals 1 to infinity also converges. So the whole series converges. So this is essentially a proof of the divergence theorem. Divergence theorem. I'm staring at the word diverge here. And so this is a proof of the integral test. So the integral test, I'll go ahead and just write this for posterity. You have it here on page 462 of your text. I'm going to go ahead and just record it here. So we need, and the statement in your book, as I'm going to write it down here, I'll just discuss what's different from what I've said. So let f be a function. So let's say decreasing positive function. Yes, I should have said, yeah, I did say it's a positive function up here. Okay, so f is a decreasing positive function. And now the difference here, your book says for all x greater than c, and c is some constant. And then the two statements here are if the integral from c to infinity f of x dx converges, then the sum of f of k equals 1 to infinity converges, and b if c to infinity f of x dx diverges, and then the sum from k equals 1 to infinity of f of k diverges. Okay, so the point here is that that we only care again about the tails, so we could really start things at some constant c. And notice here that even though we're starting at c, right, even though we're starting at c, we get to make some conclusion about our series starting at 1, right? So, so I just wanted to kind of point that out, and the reasoning is, again, because for convergence reasons, for both improper integrals and for series, we care about end behavior. And I'll just point out here, I've stated this, I've used f of k here for the series terms. Your book kind of just writes it as a sub k and then states f of k equals a sub k here later. And so the idea is that if you see a series and the terms correspond to values of some function, then you can use this test to decide whether or not the series converges or diverges. The nice thing here is that by computing the improper integral, you get to conclude convergence or divergence, right? You're not limited in the way the divergence test was limited. So what I'd like for you to do is go ahead and stop the video and go ahead and compute decide what the integral test says about each of the following series. And so you should actually be able to do these integrals. In fact, notice that a couple of these last two here in particular, were ones that you saw with the divergence test. So you'll already know what should be happening here for this third one. But okay, so this concludes the divergence test. I will go ahead and just point out here that assignment F, I'm only going to be putting in here some book problems. I wanted to point out for some of you that had commented or that hadn't known this when I talked in office hours, the solutions to textbook problems are available online, and so you should feel free to check those. The longer explanation problems do not have solutions online, and so I am expecting that you're going through and showing your steps for all of the problems in your written work. But please do use those solutions. I'm intending for you to look and see as a gauge for if you have them correct, and if you have questions about any of the material based on those, please let me know. Drop into the MSSC tutoring that's available online. Let me know if you have any trouble using those resources, and I will look forward to working with you individually if you need anything. All right, thanks.